This is Greg Trotwine with Marine Technology TV. We're here today with Alex Phillips, the head of the Marine Autonomous Robotic Systems program here at NOC. And we're here just to talk about some of the interesting work going on at NOC and also some of the specific technology drivers. So Alex, first and foremost, we appreciate you joining us.
No problem.
Okay. To start us off, why don't you just give us a very brief career background and really just talk about your role here at NOC, what you're responsible for, and a little bit, just a background on what you're doing on a daily basis.
Okay, so I'm a naval architect by training. So I started thinking I would go and design yachts for a living. Got a little distracted and started thinking things. Probably about 15 years ago, I got involved in a student competition to design and build AUVs. And that was much more interesting than what I was doing for a real job at the time. And so, yeah, I got to build these small AUVs, do all the software, do all the hardware, do all the electronics, break them. They never really worked very well. But in that process, I got a real passion for sort of building this kind of technology. And so finished my PhD at Southampton and then effectively came down to the NOC 10 years ago to sort of run projects and build a team to sort of develop new and cool robots. 10 years later, I'm sort of heading up the facility here. So we've got about 40 marine robots and we've got about 60 engineers, computer scientists and researchers. And we're all here to sort of develop, build, operate, and go make measurements in the ocean for the sort of ocean science community.
Okay, no, that's excellent. So, Alex, again, I love being in the workshop like this because we're surrounded by all the interesting kit that it really is the basis of what we do at Marine Technology Reporter. Why don't you tell us a little bit about the NOC autonomous robotics fleet?
Okay, so we've got a fleet, as I said, of about 40 vehicles, and they vary substantially. So we buy in a lot of kit. So we buy underwater gliders. We've got a large ROV, but we also design, build, and operate the auto-sub AUVs. And these are the bit that really excite me because this is all the stuff that we do in-house. So these vehicles here, we've designed them, we've built them, we've written all the software, we've designed the control systems, we've crashed them, thrashed them, occasionally lost them. But we really understand every bit of the subs, and that allows us to really adapt them for trying to answer or gather different types of science data. Mm-hmm. So we're really able to provide really interesting capabilities to the science community to go and make measurements that people haven't done before.
Yeah, no, it's awesome. I mean, we talk about the technology all the time, but we talk about it and we write about it. You actually do it. And so when you look holistically, obviously, the evolution of technology, when you look back from when you started to where you are today, I'm sure has come quantum leaps forward. But when you look at the drivers today specifically for what the people who use these systems, what they're asking them to do, what do you count, I guess, as the key drivers?
So we see a lot at the moment around persistence, so being out in the water for longer, so whether that's deploying gliders from shore and having them operate for weeks or months, putting these vehicles, long-range vehicles, out for weeks and months, that sort of ability to get vehicles out and about without the need for a research ship, that's really quite a big driver for us at the moment. It just allows us to expand on what we can do. We can't do anywhere near everything they do with a ship with one of these, but we can do some of it. And if by doing some of it, we free the ship up to go and do the stuff we can't do, it's a win-win. On the sort of the science request side, we always see requests for under ice. A lot of the AutoSub program sort of originated with some of the under ice work in the early 2000s. So that's always a driver, and we're just seeing more and more of it, driven by the need to understand melt rate of glaciers, sea ice thinning, all of these really important problems. We're also seeing a lot more requests around the carbon cycle, so understanding how the ocean sequesters CO2, and obviously if you can put sensors onto these vehicles that can measure things like pH, total alkalinity, dissolved in organic carbon, you can start to help scientists get to grips with what's a really complicated problem.
When you look from when you started in this, and I'll call it a business. I know you're not you're not a business, but when you started in this sector and you look at the technology and then you kind of sit back and consider all the things that have gone into these vehicles to make them longer lasting, to make them better at what they do, more efficient. What technologies do you count as being the most dramatic in their impact on the efficiency of these operations?
So the really boring answer is a lot of it is just about polishing the basics.
Mm-hmm.
So actually having these systems to be robust, so you put them in the water and they work.
Mm-hmm.
And that takes a long time. Go and ask anyone who develops ocean tech, and it takes a long time to get things sort of really robust in the water. And if we're honest, we've spent a long time doing that with our tech. But now we've got a very stable, robust platform. We've got some really interesting opportunities to leverage some of the sort of the new technologies that are coming. So there's some really interesting sensor technology coming through at the moment, which is allowing us to measure new parameters. So some of the lab-on-chip type technologies that are developed here, now able to sort of put a full chemistry lab onto these vehicles to measure the nutrients and the carbon chemistry in the water column. New imaging systems that we can put onto these vehicles to either look at the plankton in the water column or count the critters on the seabed. Just that increase in sensor capability really has allowed us to tackle some new problems. But also the long-range vehicles we have, because they're a bit bigger, just allows us to stack more sensors on board. So you're not just measuring a single parameter. Now you potentially got, as I said, lots of carbonate chemistry, lots of nutrient chemistry all going on board with turbulence, with CTD. You can just build a much more capable platform. And as we're getting the more data, then you're starting to really run into things like machine learning and the need for those kind of technologies to actually deal with the data sets that are coming off the platforms, particularly around the imaging. Hopefully the days of PhD students having to go through 100,000 auto-sub images with the seabed to count the critters are gone, and we can start to use some smarter tools for that.
No, that's awesome. And again, I don't think putting something in the water and having it work properly. I know that's not boring at all to our audience. This is what they live for. So you kind of already talked about the machine learning and artificial intelligence. And I know we just had a brief chat on it. It's pervasive. It's everywhere. But I guess, can you talk holistically when you look at like AI, machine learning? How is that materially impacting the work that you do?
So we do use it in a number of areas. So we've been doing some work with Oxford Robotics Institute, running gliders up in the North Sea, where they've designed some clever algorithms to pilot the gliders and just reduce the sort of the human overload with constantly running vehicles. We use AI, as I talked about, for data interpretation. That more sits over with the science community, who sort of in the building behind me, but they use it extensively to try and deal with the data sets that we're generating. One of the areas that we're interested in is using some of the machine learning tools to identify faults on board the vehicle, because sometimes it's really hard to disentangle why a vehicle isn't going up or down in the water column. Is it the stern planes are broken? Is it the pitch sensors broken? Is it the pressure sensors broken? There's all sorts of different failure modes which can lead you to not be moving up and down in the water column in the way that you'd like to. So can you use some of the machine learning tools to do anomaly detection in the first instance? Is something just wrong? If something's wrong, can we do something about it? Or can you more accurately identify and pin down faults to particular systems so that you can react in a really sort of advisable way given the information you've got?
You're obviously these vehicles that you are responsible for helping to develop and manage and correct. They're out on, like you've already named a few, some incredible missions around the world to get that base science. When you look back over your time, was there one mission, one particular use of your vehicles that you're like, wow, that that really stand out to you personally as something that I contributed to this, or my team contributed to this to make it happen?
So I think with the auto-sub long-range vehicles, the activity we did last year as part of the NERC-funded biocarbon program. So we launched 2 ALRs from Iceland with biogeochemical sensor fits, and the ambition was to get them all the way back to Scotland. Didn't quite manage that with both vehicles. One did have to get recovered early, but the other vehicle made it all the way from Iceland to Scotland, which is quite a long way for an AUV. But what was really interesting was just the kind of science that we were doing. The sensors are on board, so it was packed full of these lab-on-chip chemical sensors. We spent a huge amount of time working with the science users to figure out what they were trying to measure, how we had to get the vehicle to operate. And so with a normal AUV, you kind of imagine them sort of flying at a constant depth or a constant altitude above the bottom. And with a glider, you manage them sort of yo-yoing through the water. With these vehicles, we were sort of doing a hybrid. We were sort of stepping through different layers in the water to make chemical measurements in different water masses. We were doing the profiling up and down to get the vertical gradients. We were chasing floats. We were meeting up with ships. We were out in the water for sort of 6 weeks. It was a really exciting activity for us, and really started to show what you can do with this kind of tech, which you can't do with some of the other technologies that were out there before.
You talked about the endurance and keeping these vehicles out here. We talk a lot about, subsea electrification, however you want to put that. Can you just kind of shed some, clarity? Are you looking the ability to keep these units out there working for as long as possible? Where are we, or can you put in perspective where we're at today, and I guess what the end goal is as far as keeping them powered, keeping them out, keeping them persistent?
Yeah, so it's a really interesting question, and there's sort of 2 approaches out there for this sort of persistent AUV operation. You've got sort of more hover-style vehicles that are docking onto the seabed and recharging, and so that's how they sort of keep their energy supplies up. We've sort of taken probably a much simpler approach, where we just pack the things full of primary batteries, just to get that long endurance. And we go for low power sensors, we go through the water slowly, and by managing that energy budget, you can potentially sort of eke out one of these vehicles to sort of 6 months operation. But then you're into a whole load of new pain, so biofouling and corrosion and all of these other issues which you haven't worried about for a sort of 2-week deployment suddenly become really important to solve.
Yeah, no. Alex, I genuinely appreciate your time. Thank you.
Thank you.